Welcome back. This is Hierarchy Education, and today we will be talking about rational exponents and properties of exponents. The following is an overview on how we will be covering today's topic. Let's start by reviewing our properties of exponents. Our first property is the power of a power property, which states that if I have some number a raised to some exponent, we'll call that exponent m, and this is raised again to the nth power, this would be equal to a to the m times n. A good example of this would be using, say, 2. If we use 2 and we raise 2 to the second power and then raise that again to the third power, this property states that this would be equal to 2 to the sixth. We can see that by taking 2 to the sixth and actually solving that out. If we take 2 times 2 times 2, and we do this 6 times, we can see that 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. Likewise, if we go in here into our 2 squared, we can see that 2 squared is 4. And if we cube that, we get 4 times 4 times 4. 4 times 4 is 16, times 4 is 64. We can see that these are equivalent statements. Our next property is the product of powers property, which states that if I have some number a to the mth power to some exponent, and we multiply that by the same base a, the same number a, to a different exponent, doesn't have to be m, but it could, we'll call that n, this would be equal to a to the power of m plus n. States that we add exponents when we multiply numbers that have the same base but different exponents. An example of this would be like using 2 to the power of 2 and multiplying that by 2 to the power of 3. This property states that this would be 2 to the 2 plus 3, adding both of their exponents together, which would be 2 to the 5th power. A way that we can see that is by calculating 2 to the 5th power. You can verify for me, but 2 to the 5th power is 32. Likewise, 2 squared is 4, and 2 to the 3rd power is 8, and 4 times 8 is 32. So we can see that we still get equivalent statements. The next property is called the quotient of powers, and this states that if I have some number a to the mth power, again to some exponent, and we divide that by the same base, some number a, to a different exponent, we'll call that exponent n, this is equivalent to a to the m minus n. We subtract the exponents, so we keep the same base and subtract the exponents. An example of this would be something like 2 to the 3rd power divided by 2 to the 2nd power. This property states that this would be equal to 2 to the 3 minus 2, which is equal to 2 to the 1st power, which is just 2. A way that we can verify this is by looking at 2 cubed. 2 to the 3rd power is 8, and 2 to the 2nd power is going to be 4. 8 divided by 4 is 2. So again, we can see that we have an equivalent statement, a true statement. The next property we have is called the power of a product, and this states that if we have two numbers, a and b, and they are being multiplied against each other, and they are to the same exponent, say the mth exponent, this would be equivalent to a to the m times b to the m. An example of that would be using, say, 2 and 3 for a, so let's say that's 2 times 3. And we raise that to the 2nd power. This property states that this is equal to 2 squared times 3 squared, which is equal to 4 times 9, which again is equal to 36. We can verify that this is true by, instead of applying this property, just multiplying our quantity in the parentheses. So 2 times 3 is 6, and that is being squared, and 6 squared is 36, and we can see that we have a true statement. The last thing that we're going to cover is how we can rewrite a radical using a rational exponent. That is that if we have the nth root of some a value to the mth power, this can be rewritten as a to the m over n. An example of this would be like the cube root of 7 squared. This can be rewritten as 7 to the 2/3. Or the square root of 11 to the 7th power. This can be rewritten as 11 to the 7 over 2. Let's go ahead and give that a shot by rewriting some radicals using rational exponents. Go ahead and pause the video here and give these problems a shot. And here are your solutions. As you can see that we have the square root of 3 to the 9th. Whenever there isn't a number written into our index, it is assumed to be a 2. So we should have 3 to the 9 over 2, since 3 is to the power of 9. For number 2, we should have 4 to the power of 12 over 5. We can see that from our m and our n value. For number 3, we should have 12 to the 10 over 3. For number 4, we should get 8 to the 3 over 7. For number 6, or for 5, we should get 6 to the power of 5 over 10. But notice that this particular exponent, 5 over 10, can be simplified. So we will simplify that and make that 6 to the 1/2. And then for number 6, when we don't have a power of a number, that power is 1. So we know that by default there is a 1 there, so we should have a to the power of 1 over 4. And finally, moving on to the last part of our video, where we are going to be solving some problems using the properties of exponents that we covered earlier in the review portion of the video. Let's go ahead and start with our first problem here, in which I have 5 to the power of x over 3 times 5 to the power of x over 4 is equal to 5 to the 5th power. It's important to note that the goal of this problem is to find the value of x in which the left side, the entire left side, will be equal to 5 to the 5th power. We want the left side to be equal to the right side. We're going to use our properties of exponents here. What I'm going to note is that I have 2 of the same bases. I have a 5 and a 5 being multiplied by each other, and this tells me that I'm going to be using the product of powers property, which states that I can add their exponents. So I should have 5 to the x over 3 plus x over 4. That's just taking both of their exponents and adding them, and this is equal to 5 to the 5th power. Now I can note again that I have the exact same bases on both sides, and the only thing that's different between them is their exponents. That must mean that the only way that this can be a true statement is if the exponent of the left side was equal to the exponent of the right side. So we're going to ignore these 5s for a little while, and we're just going to set the exponents equal to each other. Because again, if they are equal to each other, and when they are equal to each other, that's when we'll have a true statement. So let's go ahead and add both of these fractions together. I see that they have a common denominator at 12. So on this one, I'm going to multiply top and bottom by 4. Whoops. And on the other fraction, I'm going to multiply top and bottom by 3, and that's going to give me 4x over 12 plus 3x over 12 is equal to 5. When I add these together, I should get 7x over 12 is equal to 5. And now we're just solving for x, so that's multiplying that by the reciprocal or multiplying by 12 first, which will give me 7x is equal to 60, so that's just multiplying both sides of the equation by 12. And then dividing both sides by 7 to isolate our x completely. And that gives me x is equal to 60 divided by 7. And that is the solution that we are looking for. For our next problem, let's go ahead and look at 3 to the power of x over 2 plus 1, which is equal to 3 to the negative 5x over 2. So again, what is the value of x that will make our left side equal to our right side? Now, it might look like this problem is a little bit more complicated. It's actually easier because I don't even have a property that I have to apply. I can already see that the bases are equal to each other. So the only thing that can make this problem true is if the exponents are equal to each other. So let's go ahead and set our exponents equal to each other, where we have x over 2 plus 1 is equal to negative 5x over 2, and we're just going to solve for our x. I see that I have 2 in the denominator on both sides. I'm going to multiply the entire equation by 2 so I can get rid of those denominators, and you can see that I'm going to distribute the 2 in, and that's going to leave me with an x plus 2, which is equal to a negative 5x. I'm then going to subtract x on both sides to give me 2 is equal to negative 6x, and divide by negative 6, which will give me x is equal to a negative 1/3. And that is what we are looking for. For our third problem, we're going to be looking at 2 to the power of x over 2 times 4 to the power of x over 2 is equal to 2 to the power of 6. Now, it seems like we've complicated this problem just a little bit more because the bases are not all the same. And if we don't have all the same bases, we can't apply the properties. However, we can rewrite our numbers so that way they do all have the same base, and it's going to look like 2 is going to be the base that we're looking for. So we're going to rewrite this particular 4 to be in what's known as base 2. Well, 4 is equal to 2 squared. So let's go ahead and rewrite our 4. So I have 2 to the power of x over 2 times 2 squared to the power of x over 2, and this is equal to 2 to the 6th power. Because I have 2 to the power of x over 2, this is our power of a power rule, and that states that we can just multiply these exponents by each other. So let's go ahead and do that step where we get 2 to the power of x over 2. And that'll give us 2, and 2 times x over 2, we're going to see that we get 2x. We'll get 2x over 2. So the 2's will just cancel out, and I'm left with 2 to the power of x, which is equal to 6. And now I have the same bases being multiplied together with different exponents. So this will be our product of powers rules in which we add our exponents. So I should get 2 to the power of x over 2 plus x. Whoops. This is 2 to the 6th power is equal to 2 to the 6th power. And now we can see that we have the exact same bases on both sides, and the only way that this statement can be true is if our exponents are equal. So let's go ahead and just set our exponents equal to each other, and we'll have x over 2 plus x is equal to 6. I can see that I have a fraction here with the x over 2, so I'm going to go ahead and multiply everything by 2 to make this a little bit simpler, and I'm going to distribute in this 2, and that's going to give me x plus 2x is equal to 12. So x plus 2x, that's just 3x, is equal to 12. Divide both sides by 3, and I get x is equal to 4. For problem number 4, we've got 27 to the 1/4 divided by 3 to the x4th is equal to 3 to the 6th. Here we have the same problem as last, in which we have different bases. We have a base of 27 here and a base of 3, which means none of our properties actually apply. We're going to have to rewrite this 27 to be a different base if we want to apply any properties. The good news for us is 27 is equivalent to 3 cubed. And that might take you a little bit of exploration on your end, but ultimately I think you will find that this is the direction that we want to head. So let's go ahead and rewrite 27 as 3 cubed. And we'll put that to the 1/4 power because it's still 27. And then we'll have 3 to the x4th dividing that, and this is equal to 3 to the 6th. Now we have the power of a power property occurring in our numerator, which states that we can just multiply our exponents here. And so we'll go ahead and rewrite that now, and that'll give us a 3 to the 3/4 in our numerator, divided by 3 to the x over 4, which is equal to 3 to the 6th. And so now I have the same bases with different exponents, and our quotient of powers property is going to take place here, which says that we can subtract our exponents. So maintain the base of 3, and then take our exponents, 3/4, and subtract. This is not a 6, this is a 4. And subtract our exponents. So minus x over 4 is equal to 3 to the 6th. Now I have the same bases on both the left and the right side, so the only way for this problem to be equal is if our exponents are equal, so we are just going to set our exponents equal to each other. I'm going to have 3/4 minus x over 4 is equal to 6. Let's go ahead and multiply everything by 4 so we can get rid of this denominator on the left-hand side, and that's going to give me 3 minus x is equal to 24. Subtract 3 on both sides, I get negative x is equal to 21, and multiply both sides by negative 1 in order to get x is equal to negative 21, since we want a positive x, and that is the solution that we are looking for. And for our last problem, we will be looking at 1 divided by 243 to the negative x over 3 is equal to 1 divided by 9 to the negative x over 2 plus 1. For this particular problem, this will prove a little bit more challenging for us because both of our denominators here, they don't meet at a nice point. We can see that by, let's see if we can write 243 in base 9. Let's take 9 times 9. That's going to be equal to 81. And if we multiply this by 9 again, we're going to get 729. And we can see that we've far surpassed 243. So it doesn't look like we can write 243 in base 9. However, 9 can be written in base 3 since 9 is equal to 3 squared. So there is this potential that we can write 243 in base 3. Let's find out if we can. 3 times 3 is equal to 9, times 3 is equal to 27, times 3 is equal to 81, and times 3, and look at that, that's equal to 243. So it looks like 243 and 9 are both going to have change to base 3. 243 used 1, 2, 3, 4, 5 3s to get there. So we know that 243 will be represented by 3 to the 5th power. So let's go ahead and do a quick rewrite of this problem where we have 1 divided by 3 to the 5th power, that's 243, to the negative x over 3 is equal to 1 divided by, we had to change the 9 as well, to 3 squared to the negative x over 2 plus 1. Now, what we're going to do is we are going to bring in this exponent to both the top and the bottom. A quick way of seeing that is that if you have sum a divided by b to the mth power, you can let this be equal to a to the m over b to the m. So we are going to rewrite this problem as 1 to the negative x over 3 divided by 3 to the 5th to the negative x over 3. And this is equal to 1 to the negative x over 2 plus 1 times 3, or divided by 3 squared to the negative x over 2 plus 1. The cool thing about this is that if we're looking at 1, I want you to picture 1 to any power. Regardless of what that power is, imagine 1 just being multiplied by itself or being rooted by itself. No matter what you do to it, it'll always be a 1. So we can actually just say these exponents on the numerator don't matter because whatever power that x ends up being, whatever number it ends up being, it won't matter. We will always have 1. 1 to any power is 1. I guess that could be emphasized as literally 1 to the x is just equal to 1. Nothing will change there. So we are left with 1 to the, and on these denominators, we have the power of a power property. So we're going to multiply both of our exponents on both sides. And that's going to give me 3 to the negative 5x over 3, which is equal to 1 over 3 to the negative 2x over 2 plus 2. And you're going to see that that's going to leave us here, negative 2x over 2. Negative 2x over 2 is going to be leaving us with a negative x. So let's actually go ahead and change that to a negative x. And now we can see that I have the numerators exactly the same on both sides. And the denominator, the bases are the same too. So the only way that this problem can be true is if the exponents in the denominators are equal to each other. So let's go ahead and set our exponents, the negative 5x over 3, in our denominators, let's set them equal to each other, is equal to negative x plus 2. Now I can see I have a denominator of 3 on the left side, so I'm going to multiply everything by 3 in order to get rid of that denominator. And that's going to leave me with negative 5x, which is equal to a negative 3x plus 6. I'm going to add 3x to both sides to bring together our common terms, and that's going to give me a negative 2x is equal to 6, and then divide by negative 2, which leaves me with x is equal to negative 3. And that is the solution that we are looking for.